Welcome to G Fun Facts Online. Today we are going to talk about the end of an era and the beginning of a vertical revolution. For the last 50 years, the entire semiconductor industry marched to the beat of a single drum, Moore's Law. The goal was simple: shrink the transistor, make it smaller, fit more of them onto a two-dimensional slice of silicon, and watch computing power double every 2 years. But physics has finally issued a cease and desist order. We are approaching the atomic limits of the nanometer. The cost of shrinking a transistor is skyrocketing, and the performance gains we used to take for granted are diminishing. So what does the industry do when it can no longer expand sideways? It stops looking left and right and starts looking up. We are discussing vertical 3D integration. This isn't just a packaging technique, it is a fundamental architectural revolution. Think of it as the transition of the microchip from a sprawling, flat, suburban city into a towering metropolis. By stacking active logic and memory layers directly on top of one another, engineers are unlocking bandwidths, efficiencies, and form factors that were physically impossible in the old 2D era. To understand why this is happening right now, we first need to understand the problem. It is called the interconnect bottleneck. In modern high-performance computing and AI processors, the transistor is actually no longer the primary limitation. The limitation is the wire. As we shrank transistors over the decades, they became faster, but the copper wires connecting them became thinner, more resistive, and incredibly crowded. Moving data from one side of a large 2D chip to another takes time and energy. In fact, in some of today's massive AI clusters, simply moving data consumes more energy than actually processing it. Vertical integration solves this by literally folding the 2D plane. Instead of sending a signal across a 20mm die, you send it up a few microns to the layer above. This reduces the interconnect length by orders of magnitude, slashing latency and power consumption simultaneously. There are 3 pillars of value here. First is bandwidth. Vertical connections allow for thousands of wires to connect memory and logic, far exceeding the limits of the chip's edge. Second is heterogeneity. You can stack a logic die built on a cutting-edge 2nm node on top of an I/O die built on a mature, cheaper 12nm node. This mix-and-match approach optimizes cost and yield. And third is form factor. For mobile and edge devices, footprint is everything. 3D stacking allows desktop-class performance in wearable dimensions. Now, let's get into the toolkit. How do we actually build these skyscrapers? There are 3 main technologies you need to know about. The first is through-silicon vias, or TSVs. These are the workhorses of the 3D era. A TSV is literally a vertical electrical connection, a via, that passes completely through a silicon wafer or die. Engineers etch holes deep into the silicon, insulate them, and fill them with copper or tungsten. The wafer is then thinned down until the metal is exposed on the back, allowing it to connect to another die. This is the backbone of high bandwidth memory, or HBM, where we stack 8 or 12 layers of DRAM, but TSVs have a limit on how close you can pack them. That brings us to the second, and perhaps most exciting technology: hybrid bonding. If TSVs are elevator shafts, hybrid bonding is a teleporter. Traditional stacking uses microbumps, which are tiny solder balls, to connect dies. But solder has a limit. Get too small, and it bridges, causing shorts. Hybrid bonding eliminates the bumps entirely. It polishes the copper interconnects and the dielectric insulator surface to near-perfect flatness. The 2 dies are then pressed together. The dielectric bonds instantly at room temperature using van der Waals forces. Then, upon annealing or heating, the copper expands and fuses together. This allows for interconnect pitches of under 10 microns and eventually sub 1 micron. This density is so high that you can split a single functional block, like an L3 cache, onto a separate vertical layer without a performance penalty. This is the magic behind AMD's V-cache and TSMC's IC. The third technology is the holy grail, monolithic 3D. In TSV and hybrid bonding, you manufacture 2 separate wafers and glue them together. In monolithic 3D, you build the first layer of transistors, seal it, and then actually grow a second layer of silicon crystal right on top of it to build more transistors. The challenge here is heat. Making high-quality transistors usually requires temperatures over 1000 degrees Celsius. If you heat the top layer that much, you melt the copper wiring in the bottom layer. The solution currently being researched involves cool fabrication techniques, like laser annealing, to create top-tier transistors without frying the basement. This brings us to the economy of these chips. 3D integration has given rise to the chiplet model. Instead of designing one massive system on chip that is impossible to manufacture without defects, companies are breaking the design into smaller, modular functional blocks called chiplets. This is pure yield economics. A defect on a massive monolithic die kills the whole chip. A defect on a small chiplet only kills that chiplet. It allows for a Lego-like ecosystem, where you can buy a CPU chiplet from Intel, a GPU chiplet from NVIDIA, and an I/O chiplet from a third party and stitch them together. But for chiplets to work, they need a standard language. This is where UCIe, or Universal Chiplet Interconnect Express, comes in. Specifically, the UCIe 3.0 specification released in August 2025 was a watershed moment. It introduced support for 64 gigatransfers per second, doubling the bandwidth of the previous version. Crucially, UCIe 3.0 standardized protocols for 3D packaging, defining exactly how chiplets should communicate vertically through hybrid bonds, not just horizontally. This standardization is creating an open market where 3D-ready IP blocks can be bought off the shelf. Let's shift gears to materials. For decades, chips have sat on organic substrates, which are basically high-tech, reinforced plastic. But as we stack more chips, these plastic substrates are warping and bending under the heat and mechanical stress. The solution emerging in 2025 is glass substrates. Led by Intel and followed by Samsung and SKC, the industry is pivoting to glass. Glass is incredibly flat and rigid, which is critical for hybrid bonding where even a microscopic warp prevents connection. Glass is also thermally stable. It doesn't expand and contract with heat as much as plastic, preventing the shearing of delicate vertical connections. Furthermore, you can drill much finer holes in glass, known as through-glass vias, allowing for 10 times denser connections between the chip and the motherboard. Speaking of heat, that is the biggest enemy of 3D integration. When you stack two high-powered logic chips, the bottom chip is trapped. It has a ceiling that generates its own heat. Traditional air cooling and even standard liquid cold plates are no longer sufficient for these thermal sandwiches. In late 2025, Microsoft and researchers unveiled a breakthrough in intra-chip microfluidic cooling. Instead of putting a cold plate on the chip, they etched microscopic channels inside the silicon substrate itself. Coolant flows directly through the chip, microns away from the hot transistors. This method demonstrated heat removal efficiencies 3 times greater than traditional methods, reducing peak temperatures by up to 65%. This is the key enabler for stacking high-power logic on logic. Now, who are the titans fighting for this third dimension? There are 3 main foundries. First, TSMC. Their CoWoS technology is the current king of AI, used by NVIDIA's GPUs. They also have SoIC, which uses hybrid bonding for bumpless stacking. Second is Intel Foundry. They use Foveros for 3D stacking and a technology called PowerVia for backside power delivery, which cleans up the wiring mess to make stacking easier. Third is Samsung Electronics. With their brand X-Cube, they are leveraging their dominance in memory to create tightly coupled logic memory stacks and offering turnkey solutions where they manufacture everything under one roof. So where is this going? Looking toward 2030, we see 2 major horizons. One is optical interconnects, or silicon photonics. Eventually, even copper vertical wires will be too slow or generate too much heat. The industry is moving toward co-packaged optics, where data is converted to light inside the 3D stack and shot out via optical fibers. The second horizon is neuromorphic 3D. The ultimate goal is to mimic the human brain, which is the ultimate 3D integrated circuit. Future chips will adopt synaptic architectures where memory and compute are not just stacked, but interwoven at the transistor level. In conclusion, vertical 3D integration is not just the next step. It is the only step left. The days of easy scaling are behind us. The future belongs to the architects, who can think in cubic millimeters rather than square ones. From the microscopic precision of hybrid bonding to the macroscopic shift to glass substrates, the industry is rebuilding itself around the Z-axis. We are witnessing the birth of the Hypermore era, where performance scales not by shrinking, but by stacking. The skyline of silicon is rising. Thanks for listening to G Fun Facts Online.